Chapter number 27, Way ANOVA. ANOVA stands for Analysis of Variance. What is one way? One way means single factor experiments. Can you still remember chapter number 9, factorial experiments? We defined the terms used. We didn't do any analysis. But we found the terms such as the response variable, factors, levels of the factor, and treatments. We are going to use those words today. We do not analyze any multi-factor experiments. At introstat level, we do only single factor analysis. Now, what is a factor? First, we need a response variable. Response variable is what you measure as the response in the experiment. Say, for example, I have to test the efficacy of a vaccine. I need to see the duration where that vaccine provides protection to the people against a certain virus. So the response variable could be the number of days or number of weeks or number of months, which is a different variable. Now, what possible causes can affect that response variable? We define anything that can affect the response variable as a factor. For example, let's say gender. Whether the person is male or female might affect that response variable. So gender can be considered as a factor. How many levels does it have? There are two levels of the factor gender. One level is male, the other level is female. And another possible factor could be the age group. I can have several age groups. Let's say my age groups are 0 to 10, 10 to 20, 20 to 40, and 40 to 60, and above 60. So I have 5 age groups. So age is a factor in that case, and I have 5 levels of that factor. Any specific combinations of those factor levels are called treatments. For example, male age group 0 to 10 is a treatment. For another example, female above 60. Female is the level from the factor gender, above 60 is a level from the factor age group. Now that combination is a treatment. Now when you do not have multi-factors, if you have just a single factor, then the levels of that factor are called treatments. Today we analyze the simplest case where I have just a single factor. The levels of that factor should be more than 2. If you have just 2 levels of that factor, I can simply use the 2-sample z-test or the 2-sample t-test. I can use 2-sample z-test if I know sigma 1 and sigma 2. I can use 2-sample t-test if I don't know sigma 1 and sigma 2. We have completed those discussions earlier. Let's go to point number 1. The purpose of multiple mean comparison. Let's say there's a certain product. We will assume that there are 3 brands already existing in the market. 3 brands are already existing means in terms of product characteristics such as the quality, durability, taste, color, packaging, and also price, and so on, they should be equal to each other. Otherwise, 3 brands cannot survive in the market for a specific product. Let's say the true mean of a specific product characteristic is given by mu, and mu sub 1 for the first brand, and mu sub 2 for the second brand, and mu sub 3 for the third brand. And they are all surviving in the market means mu 1 should be equal to mu 2 should be equal to mu 3. Let's say I would like to make that same product with a different brand name. Before entering into the market, I should make sure that my product is also at least equal in terms of product characteristics to the other existing products. Let's say that true mean of the product characteristic of interest is mu 4 for my product. Now I have to see if mu 1 is equal to mu 2 is equal to mu 3 and is also equal to my product mu 4. If all these means are equal to each other, then I can conclude that my product may also have a place in the market. So likewise, there are so many cases where I would like to compare more than 2 means at a time. Let's say 3 means or more than 3 means. To compare those things, I need a proper scientific tool. We are going to study that proper scientific tool today, and it's called single factor analysis of variance. We do single factor because we only can compare just one factor at interested level. At higher statistics levels, you can compare multi-factor experiments. But on the other hand, there's another small catch. Any multi-factor experiment can be remodeled and analyzed using single factor procedures. Let's say I have two factors. Factor 1 has 3 levels. Factor 2 has 4 levels. Altogether, there are 3 times 4, 12 treatments. If I define a new factor which has 12 levels, then it becomes a single factor experiment. So that multi-factor experiment can also be analyzed using the methods discussed in this class after remodeling it as a single factor experiment. That part is not expected from our students. So you will be given a factor explicitly with its levels, and you have to simply analyze that single factor experiment in your homework and in your exams. So today we are going to learn the techniques of doing that analysis. Let's go to point number 2. How do you write down the null and the alternative hypothesis? The first thing is to write down the null hypothesis. When you have more than 2 means to be compared, that means when you have 3 or more than 3 means to be compared with each other, this is how you will write down your null hypothesis. First thing, even before writing down the null hypothesis, is that you must define all the means explicitly. Let's say we have n number of true means to be compared in general. I have to compare mu1, mu2, mu3, and up to mu_n. You must define each mu explicitly. For the example that I discussed earlier, it could be the true mean durability. And we said there are 3 existing brands. So mu1 could be the true mean durability for brand 1, mu2 could be the true mean durability for brand 2, and mu3 could be the true mean durability for brand 3. And then I have to define a mu4 for my product. That will be the true mean durability for my brand. So in that case, I have to compare 4 groups. I have up to 4 means. This n will be 4 in that case. So the null hypothesis can be written as all means are equal. You can write it in words or you can write it in symbols using this way. mu1 equals, mu2 equals, mu3 equals, if you have the 4th one, mu4. And if you have up to n, just like this, you can write them as that. Of course, writing it like this is always very easy. Don't go for just n for all these cases. Read your question. If your question has 3 means to be compared with each other, you have to stop at 3. If your question has 4 means to be compared, you must write 4 means. Okay? Don't go up to nth mean. I will take points off if you write this generic form. And then we have to know how to write down the alternative hypothesis. When I have my null hypothesis this way, the alternative hypothesis means at least one of these conditions is violated. That means at least one true mean is different from the other true means. That's how you will write your alternative hypothesis. We can write it in words. That's very easy rather than using the symbols. So I will simply write it in words this way. At least one true mean is different from the other true means. So we will develop a test statistic to see if the null hypothesis is true or false. If our test statistic says that the null hypothesis is incorrect, that means our data support this alternative, and we will have to interpret as that. That means I have statistical evidence with whatever the specific probability, often for our cases 95%, to conclude that at least one true mean is different from the other true means. Rather than just writing it as true mean, make sure to use the name of the random variable given as well. On the other hand, if our test statistic says the null hypothesis actually is true, that means our data do not support this alternative. In that case, we will interpret this as we have no evidence, because of this, to conclude at least one true mean is different from the other true means. Once again, make sure to use the variable name with true mean term. Well, at that step, there's a very natural question. If my data indicates that at least one true mean is different from the other means, which mean could it be? To answer that question with proper scientific tools, we will need a little bit more statistical knowledge. There are sophisticated tools such as Fisher's least significant difference. And also there's another one called Tukey's honest significant difference. We do not discuss those things at introstat level. One reason why we don't discuss those things is that there are some specific other distributions that are necessary to go for those calculations, and we haven't discussed those distributions on the introstat level. And the other reason is there are some simpler ways at introstat level to determine which mean could it actually be if this alternative is supported by our data. For example, you can try to draw the box Whisker plot. If I have 4 groups, you can draw 4 box Whisker plots. Let's say this is one box Whisker plot. Can you still remember this? This is the lower limit. This is Q1. This is median. This is Q3. This is the upper limit. Let's say this is how it is for group 1, which corresponds to mu1. I would say group 1. We will also draw for the second group. This may be for group 2. And we also draw it for the third group. This is for group number 3. And we also draw it for fourth group. This is for group 4. So if our data indicates that this alternative is true, when you draw all the box Whisker plots on the same axis, of course, this is your x-axis, this is your y-axis, you will see at least one box Whisker plot is significantly away from the other box Whisker plots. In that case, we can see that this one, group 3, has the mean which is significantly different from the other means. Sometimes 2 of these box Whisker plots may be significantly away from the other 2. That means there are 2 means that are different and there are 2 means that are equal to each other. That's one simple way to visualize which mean is different if our data indicates that the alternative holds true. On the other hand, for practical purposes, let's go back to that example that I initially mentioned. There are 3 brands existing in the market. We agreed that they exist because they are equal in product characteristics. If our test indicates that at least one true mean is different from the other means, most likely it should be the true mean of the newcomer for that product. At introstat level, you do not have to go to that next step. We stop here. Let's go to point number 3. Why a collection of t-tests not recommended for multiple mean comparison. That means instead of writing all of these means to be equal to each other like that and writing down the alternative this way, what if I compare the 2 means, mu1 and mu2, using the 2-sample t-test? What if I compared mu1 and mu3 using the 2-sample t-test? Likewise, I can continue to do so, mu1 and mu4, up to mu1 and mu_n. And then I can start that process again from mu2. I can compare mu2 and mu3, mu2 and mu4, and I can go up to mu2 and mu_n, and I can start that process again with mu3, compare mu3 and mu4, mu3 and mu5, and so on. So what if I do a collection of 2 sample t-tests instead of performing one hypothesis test for these kind of null and alternative hypotheses? Well, obviously, one problem is that procedure is inefficient. You are doing so many tests so many times, and it takes time, and it's a waste of resources. On the other hand, there's another technical, mathematical drawback. As you know, with each test, we compromise a certain level of accuracy as type 1 error, which is given by alpha. We always take alpha as 5%. For each test, we only have 95% confidence. That means we allow 5% error, type 1 error. So when you do so many tests, what we do is we actually allow more and more error. Well, the error will not be added linearly. So doing one test is 5%, but it does not mean doing 2 tests is 10%. Doing 2 tests will be more than 5%, even though it doesn't go up to 10%. Doing 3 tests will be even more error than doing 2 tests. So likewise, we keep adding error more and more with each iteration of a new test. Therefore, we must avoid that situation. Those are the reasons why we do not perform a collection of t-tests instead of a single test for multiple mean comparisons. Let's go to point number 4. We need a test strategy. We are practically comparing the true means, but the chapter title is Analysis of Variance. Why do we need to analyze the variance if I have to compare the true means? There's a reason. We will see that reason through an example. We will write it down under point number 4. Let's say we have 3 levels of a factor to be compared. I will label them as group 1, group 2, group 3. I can also label them as level 1, level 2, and level 3. But those terms are not used, at least in your calculator or in MS Excel. The MS Excel uses the terms groups. So I will use that for this example. So I will label them as group 1, group 2, and group 3. Well, just 3 groups are enough for this example. We already have 3 means, 1 from each group, which is more than 2 means, and that's where we see the analysis of variance. So we will also let mu1 be the true mean that corresponds to the population of group 1. We will let mu2 be the true mean that corresponds to the population of group 2. And we will let mu3 be the true mean that corresponds to the population of group 3. Of course, our null hypothesis will be mu1 equals mu2 equals mu3 for this case. The alternative hypothesis will be at least one true mean is different. From the other true means. I will give you the data set. Let's say group 1 has the data points like this. I have 20.1, 20.2, 19.8, 20.0, and 19.9. I have collected 5 data points from group 1. From group 2, let's say these are the data points that I collected. 25.1, 25.1 again, 24.9, 25.0, and 24.9. And again, I have 5 data points. And let's say group 3 has the data points like this. 30.2, 30.1, 30.0, 29.8, and 29.9. Once again, I have 5 data points. When you have 3 groups, and from each group, when I have the same number of data points, that design is called what? It's a balanced design. Balanced designs are the best form of designs for statistical testing. They have the best power. Now, based on this data set, what will you say about your null hypothesis? Will you accept your null hypothesis or will you reject your null hypothesis? Very clearly, we can reject our null hypothesis based on this data set. That means we can conclude that our data support this alternative. That means we can say we have statistical evidence to conclude that at least one true mean is different from the other true means. Of course, just by looking at this data set, we can say that all 3 means are different from each other. Very clear, because all the data points in group 1 are very close to 20. All the data points in group 2 are very close to 25. All the data in group 3 are very close to 30. That statement itself explains everything about the test we are going to perform. What do we mean by all the data points are very close to 20? I can calculate the group mean. Let's say the group mean is given by x bar 1. That group mean is equal to 20 for this data set. Now, with respect to 20, all these data points are very close to each other. And the same way, I can calculate the group mean for the second group. Let's say it's x bar 2. The group mean for the second data set is equal to 25. All the data points in the second group are very close to 25. And we can calculate the group mean for the third group. That's equal to 30. All the data points in third group are very close to 30. And if you compare these 3 values as 3 data points, they are very different from each other. Right? So if we can observe those 2 characteristics, then we can safely say the null hypothesis should be rejected. So what are those 2 characteristics? The variability is considered. These can be considered as the variability between groups. Variability between groups should be large. The variability within group should be small. Variability is measured using variance. That's one of the best statistics we have to quantify the variability. So we will write it down using variance. We will say variance between groups this should be large. And variance within groups that should be small. If that happens, we can reject our null hypothesis. Okay? I would say reject H0 if these 2 conditions happen. Now, how large and how small? We need a certain boundary for those. For example, if the variance between groups is equal to 10, well, 10 can be large compared to 1. If the variance within groups was equal to 1, then that previously calculated 10 can be considered large. On the other hand, if the variance within groups was equal to, let's say, 9, in that case, 10 cannot be considered large. So we need to combine these two rather than just looking at them separately. To combine those two, we are going to define a new test statistic. I will say we will reject the null hypothesis, reject H0 if the ratio between these two, variance between groups divided by variance within groups, if that ratio is large, because we said we reject the null hypothesis if the variance between groups is large and variance within groups is small. So if this is large compared to this small, then the ratio between these two should be large. Now I have one quantity. So I will say reject the null hypothesis if the variance between groups divided by variance within groups. If this is large, we reject our null hypothesis. Reject if this is large. Now once again, I will need a numerical value for that. How large? Now if this ratio is, let's say, larger than 3, can I go ahead and reject? Or should I look for this ratio to be larger than, let's say, 10 to reject? So how large should it be in order to reject the null hypothesis? What is that boundary value? I just need one boundary value. To determine that boundary value, I will need the distribution of this statistic. Now what is the distribution of that statistic? Well, we will see what it is. But there's one thing for sure. It's a positive only random variable. Variance is always positive only, right? How do you find variance? Variance is found by using this equation. Variance is a summation of data points minus their means squared divided by n minus 1. Remember? In fact, the label we used for variance was S squared. We used S squared because variance is always positive. Now we know this ratio is positive only. And let's say the distribution of that ratio looks like this. Because this is a positive only distribution. This is 0 and this is x-axis, this is y-axis. So I have a positive only distribution. Now when I know this distribution, I can keep that type 1 error on the right tail of this distribution. I can keep complete alpha on the right tail. And I can find this value as the critical value. Now I can assume that this critical value is the point which determines whether this ratio is large or small. If this ratio is found to be on this shaded interval, let's say somewhere here, then I can reject our null hypothesis. If it's in unshaded interval, I should accept the null hypothesis. Now, all I need is to figure out the distribution of this ratio. Let's go to point number 5. If the data are normally distributed, then the distribution of variance. That's very important. The methods discussed in this section will be limited to the case where our data points are all normally distributed. If they are not normally distributed, the methods discussed today cannot be applied. Analysis of variance, the test procedure you will see today, is only applicable for normally distributed data. Please keep that in mind, that's very important. Okay, before going to the ratio between two variances, I need to find the distribution of variance. Of course, here's the equation for variance. X values are normally distributed. I have subtracted their sample mean and I have squared them and take the summation. What should be the distribution? Well, if I have a standard normal random variable, if I square it, what's the resulting distribution? We discussed that at the beginning of the semester. We said if you take a standard normal random variable and square it, the resulting distribution is a chi-squared distribution with 1 degree of freedom. If I have more than one standard normal random variables, and if I square all of them and add them up, let's say I have n number of standard normal random variables. I squared each of those n standard normal random variables. Then I take the summation. Then the resulting distribution is a chi-squared n distribution. Variance has a similar characteristic. This guy is the numerator. Look at this numerator. I have normally distributed x. I have, of course, subtracted their sample means. And then I have squared. And then I have taken the summation. Of course, this numerator should be a chi-squared random variable. So variance is actually written as sums of squares, because this is a summation, these are the squares, that divided by n minus 1. Now what is n minus 1? What's a specific scientific name that we gave for n minus 1? N minus 1 is always called the degrees of freedom, right? So variance is also equal to sums of squares divided by degrees of freedom. Because variance is written as sums of squares divided by degrees of freedom, variance is also called mean squares. These terms are actually used in MS Excel. You will see when we do a data analysis using MS Excel for multiple mean comparison. Now, what we saw just a minute ago was the distribution of sums of squares. Sums of squares has chi-squared distribution with its corresponding degrees of freedom. Now we can use this information to figure out this ratio. This ratio has a variance on the numerator and another variance on the denominator. Variance in the numerator is variance between groups. Variance between groups can be written as sums of squares between groups divided by degrees of freedom between groups. The denominator has another variance, which is the variance within groups, which can be written as sums of squares within groups divided by degrees of freedom within groups. Sums of squares within groups divided by degrees of freedom within groups. Now, you must know this distribution. Take a chi-squared random variable divided by its degrees of freedom. Everything is divided by another chi-squared random variable and divided by its degrees of freedom. What's the distribution of this ratio? Chi-squared random variable divided by its degrees of freedom, everything divided by another chi-squared random variable divided by its corresponding degrees of freedom. That gives us F distribution. So this is called an F test statistic. I will write this as F test. F distribution has two degrees of freedoms. One is called the numerator degrees of freedom. The other one is called the denominator degrees of freedom. So this can be labeled as df1. This can be labeled as df2. So this is written as distributed as f df1 df2, where df1 stands for the numerator degrees of freedom and df2 stands for the denominator degrees of freedom. Once we know this distribution, when we have alpha, we can determine the critical value. So we will first see how to find degrees of freedoms. Now what should be df1 for this example? df1 is defined as degrees of freedom between groups. between groups, I have three groups. To calculate this variance between groups, I have to use these three numbers. That's it. Use these three data points and calculate the variance. So, what should be degrees of freedom between groups for this example? I have just three groups. Degrees of freedom is always defined as n minus 1. Therefore, for this example, df1, degrees of freedom between groups, should be 3 minus 1, which is equal to 2. So we figured out the numerator degrees of freedom for this example, which is f2. Now I need within group degrees of freedom. Within first group, I have 1, 2, 3, 4, 5 data points. So within first group, I have 5 minus 1 degrees of freedoms, 4 degrees of freedoms. The second group also has 5 data points. Once again, n minus 1, which is 5 minus 1, I have 4 degrees of freedoms. Within third group also, I have 5 data points. Therefore, degrees of freedom should be 5 minus 1, which is equal to 4. So, the total within group degrees of freedom is 4 plus 4 plus 4, which is equal to 12. So, the denominator degrees of freedom for this example is 12. It's very important to remember how to find these 2 degrees of freedoms. Of course, on the other hand, once you entered the data into your calculator, it will also give you these degrees of freedoms. You can simply read it from the calculator output if I have given you the data set. But there are occasions where I will simply tell you how many data points are in each group and how many groups you have. In that case, you will have to figure out the 2 degrees of freedoms yourself. To do that, please remember this process. All right, so once I have these 2 things, I can go for the F distribution table. I have to go for this specific F distribution, F2, 12. And then I will keep complete 5%, 0.05 on the right tail of that distribution. And then I will need to find this value, which is the critical value that should be used in this experiment. Okay, let's go to F2, 12 distribution with alpha equals 5% and figure out the critical value.
So far, in order to find all the critical values, we've been using the TI-84C E+ calculator. We can access distributions and then select the corresponding inverse distribution function. But unfortunately, your TI-84C E+ calculator still does not have inverse F distribution. Therefore, in order to figure out the F critical value, you will have to go for the traditional F distribution table. What you can see on the screen is one such traditional F distribution table. F distribution tables are available for popular values of alpha, such as 1%, 5%, 10%, and so on. This specific table is corresponding to alpha equals 5%, or in other words, 0.05. If you are interested in F distribution tables of any other alpha values, you can simply Google them. However, for all the calculations of this class, we use alpha equals 5%. Therefore, this is the F distribution table you will need for all of your homework and also for your exams. To read the F critical value using the F distribution table given here, you simply have to look at the 2 degrees of freedoms. The first row indicates the numerator degrees of freedom. The first column on the left indicates the denominator degrees of freedom. You simply have to match the numerator degrees of freedom and denominator degrees of freedom. And then from the body of this table, you can read the corresponding critical value. For the example we are working on, the numerator degrees of freedom is equal to 2 and the denominator degrees of freedom is equal to 12. So if I match those 2 numbers, it corresponds to this value right here. The F critical value we need is equal to 3.885.
We saw that the critical F value for this example is 3.885. So this value is 3.885. And then, of course, we can easily calculate variance between groups and variance within groups and take the ratio between those two. Well, we will not do it that way. We will simply enter our data set into our calculator, and then your calculator has analysis of variance F-test inbuilt. And then we can run that test, and it will give you the F-test statistic in a single step. If that test statistic is larger than this critical value, then we can reject our null hypothesis. If we reject our null hypothesis, our data support this alternative. In that case, you will have to interpret the fate of the alternative. I would say we have statistical evidence with 95% probability to conclude at least one true mean is different from the other true means. In case, if our test statistic was landed on the unshaded interval, in that case, I cannot reject the null hypothesis. We will have to accept the null hypothesis, and our data will not support this alternative. If so, we will have to interpret it as we have no evidence to conclude at least one mean is different from the other means. But of course, for this data set, you will never get an F-test statistic which is going to be on the unshaded interval. Please write down this equation under point number 6 of your posted lecture note. If you read point number 6 again, distribution of the ratio between group variance and within group variance. In front of the term between groups, I have also written down in parentheses as factor. In front of within group, I have written down in parentheses the term error. Those are the two terms used for between groups and within groups in your TI-84 calculator. Use of the term factor is not correct for the factor levels. We analyze only single factor experiments. So these are called levels of that single factor. So it should be actually labeled as levels rather than factors. In fact, TI-84 only has single factor experiment. So for single factor, it's incorrect to write it as factors. However, your calculator uses the term factor for the levels of the single factor. But MS Excel, on the other hand, uses the term group. MS Excel uses the term within groups for the data points inside each group, and your calculator uses the term error. Of course, the term error is not very incorrect. It makes sense because mu3 is the true value for the third group. Now, the variability found in each data point is due to some error. So in that sense, the use of the term error makes sense. When you run ANOVA F test in your TI-84 calculator, the very first thing you will see is the F-test statistic. After that, you will see the term factor. Under factor, you will see few numbers given. One of them is DF. Factor DF corresponds to the numerator degrees of freedom for your data set. For example, for this data set, it is 2. And if you scroll down further, you will see some other things classified under the term error. If you read DF, which is degrees of freedom, written under error, that corresponds to the within group degrees of freedom for your data set. For this example, it is 12. Let's go to point number 7, test procedures. So far, for all the previous hypothesis tests, we had 3 methods. We had the confidence interval method, we had the test statistic and critical value method, and we had the p-value method. Well, of course, confidence interval, maybe we can construct a confidence interval if I have to compare only one true mean, because I can construct a confidence interval for that one true mean. And if I have to compare 2 population means, I can still construct a confidence interval for the difference between the 2 means. But when I have to compare more than 2 population means, then there is practically no way that I can construct a confidence interval addressing all those means. Therefore, we say there is no confidence interval approach for single factor analysis of variance F-test. We only have 2 approaches. One approach we already saw, that is the test statistic and critical value approach. F-test is always only a right-sided test because we rejected the null hypothesis only if this ratio is large, which indicates that this null and alternative hypothesis are tested only as a right-sided test. And then if you go for the p-value, how do you calculate the p-value? P-value for a right-sided test. First, I need the test statistic. Once we have the test statistic, I can find area to the right from that test statistic in its corresponding F distribution. To find that, if you need, you can use FCDF in your calculator. But on the other hand, if you have the data set, if you entered that into your calculator, and if you run ANOVA F test for that data set, it will also give you the p-value in addition to the F test statistic. So you can simply read it from the calculator. But there are some cases where I will not give you the data set. Instead, I will tell you what should be the F test statistic, and I will also give you some information for you to figure out degrees of freedom for numerator and degrees of freedom for denominator. And I will ask you to calculate the p-value. In that case, you have to find the area to the right from the given test statistic of the corresponding F distribution using FCDF distribution in your calculator. You can go to distributions and select FCDF for that calculation. Then you must enter the calculated F test statistic as the lower limit. The upper limit is something positive and large, like 100 million. And then you will have to define df1 and df2. And then select paste and hit enter. That should give you the p-value. If this is your critical value, and if your test statistic is somewhere here, we reject our null hypothesis. The p-value is defined as area to the right. So this is your p-value. So the p-value procedure is very similar to the p-value used in previous examples. We reject our null hypothesis if the p-value is lesser than alpha. Very straightforward. Let's go to point number 8. There's an example given. Please go ahead and read and see if you can answer part A and C. Point number 8, an experiment was run to determine whether 4 specific firing temperatures affect the density of a certain type of brick. The experiment led to the following data. So you have the data set given. There are 4 specific firing temperatures. Firing temperature is the factor. The 4 given levels are the levels of the factor. Part A, write down the null and the alternative hypothesis to be tested. Define all the terms used. So I have 4 different firing temperatures. For each firing temperature, I must have a true mean. So we will let mu1 be the true mean density at firing temperature 100 degrees Fahrenheit. The same way, I will let mu2 be the true mean density at firing temperature 125 degrees Fahrenheit. We will let mu3 be the true mean density at firing temperature 150 degrees Fahrenheit. We will let mu4 be the true mean density at firing temperature 175 degrees Fahrenheit. Then we must write down the null and the alternative hypothesis. So the null hypothesis should be written this way. There are 4 means, so I will write mu1 equals mu2 equals mu3 equals mu4. The alternative hypothesis is written in words. We can say at least one true mean density is different from the other true mean densities. At least one true mean density is different from the other true mean densities. That's the complete answer for part A. If you do not define these things, I will take points off. Part B, we will come back to that. But for now, we will straight away go to part C. The reason I need to skip part B for now is because your calculator will also give you the degrees of freedom for numerator and degrees of freedom for denominator. But rather than copying those two degrees of freedoms, we will look at the data set given and see if we can figure out the degrees of freedoms. Part C says, what are the critical F value and the rejection region for the null hypothesis at alpha equals 5%. To figure out the critical value and the rejection region, I first need the degrees of freedoms. So we will first answer part C. We will write part B here and we will write part C there. I need F distribution. If you remember the F test statistic, the numerator is variance between groups. The denominator is variance within groups. So the numerator degrees of freedom should be the degrees of freedom between groups. I have 4 groups. So degrees of freedom between groups should be 4 minus 1, which is equal to 3. 3 is the numerator degrees of freedom. Now we have to look at the number of data points in each group. We have to subtract 1 from the number of data points in each group to figure out the degrees of freedom within each group. For the total degrees of freedom within groups, I have to sum them up. So the first group has 7 data points. That means from the first group, I get 6 degrees of freedoms. The second group has 4 data points. So from the second group, I get 3 degrees of freedoms. The third group also has 4 data points. Therefore, from the third group also, I get 3 degrees of freedoms. The fourth group has 6 data points. Therefore, from the fourth group, I get 5 degrees of freedoms. So summation of all these should be equal to the total within group degrees of freedom. This is 9 plus 3 is 12 plus 5 is 17. So this is the distribution I should use to find the critical value. So here's my F317 distribution. I keep complete alpha on the right tail. And this value is the F critical value. The calculator does not have inverse F function. Therefore, we have to go for the traditional F distribution table. Let's do that.
This is the F distribution table for alpha equals 5%. The numerator degrees of freedom is equal to 3 and the denominator degrees of freedom is equal to 17 for the example we are discussing. So I simply need to match 3 and 17, which is right here. The critical value we need is 3.197.
We saw the critical value is 3.1968. The rejection region is therefore from 3.1968 to positive infinity. We can also write that as a part of the answer because we should also give you the rejection region, which is 3.1968 to positive infinity. Now we can go back to part B. To find the F-test statistic, we will enter the given dataset into TI-84 calculator.
This example has 4 temperature groups and each temperature group has density readings. So those 4 groups will be entered into the lists L1, L2, L3, and L4. So let's go to Stat, Edit, number 1, Edit, hit Enter. I'm going to enter all the density readings corresponding to temperature 100 degrees into the list L1. The first reading is 21.8. The second reading is 21.9. The third reading is 21.7. The next reading is 21.6, and the next reading is 21.7. The next reading is 21.5, and the last reading is 21.8. And then I will enter all the density readings corresponding to the temperature 125 degrees into the list L2. The first reading is 21.7. The second reading is 21.4. The third reading is 21.5. The fourth reading is 21.5 again. And similarly, I will enter all the density readings corresponding to temperature 150 degrees into the list L3. The first reading is 21.9. The second reading is 21.8. The third reading is 21.6, and the fourth reading is 21.5. Now we will enter all the density readings of the last temperature group, which is 175 degrees group, into the list L4. The first reading is 21.9. The second reading is 21.7. The third reading is 21.8. The fourth reading is 21.7. Fifth reading is 21.6, and the sixth reading is 21.8. Please note that 100, 125, 150, and 175, they are not data points. They are just group labels. So I have not entered those numbers anywhere into the calculator. In each group, I have density readings. Those are the values that I entered into the lists L1, L2, L3, and L4. Now we can calculate the F-test statistic. For that, you have to press Stat, select Tests, and then you have to select the last one in the list of tests. The shortcut to select the last one is the upper arrow key. You can see H ANOVA. Select that and then hit Enter. All you have to do at this step is to define the lists where you entered your data separated by a comma. We entered our data into the lists L1, L2, L3, and L4. So we will first write it as L1, which is second one, and then you have to write a comma. Comma is right here. And then second 2, which is L2, comma again, and then L3, which is second and 3, and then comma again, second and 4. And then I can close parentheses, and that's basically all you need. Then you can hit Enter. Here is the output for Way ANOVA. The F-test statistic is given on the first line. The F-test statistic is 2.4527. The p-value is given on the second line. The p-value is equal to 0.0986. As indicated earlier, TI-84 uses the terms factor and error for between groups and within groups respectively. You can see degrees of freedom under factor is given as 3, which is the degrees of freedom between groups. You can see that error degrees of freedom is given as 17, which is the within group degrees of freedom. That indicates that we have to use F317 distribution for the critical value.
We calculated the F-test statistic, which is equal to 2.4527. Let's go to part D. Test the hypothesis using the test statistic and critical value method. Using your answers to parts B and C, clearly interpret the test result in the context of the problem. Now, based on this F-test statistic and this F critical value, what's your decision? Are you going to reject your null hypothesis, or are you going to fail to reject your null hypothesis? Of course, the calculated F-test statistic is 2.45, which is not in the shaded interval. 2.45 is somewhere in the unshaded region of this distribution. Therefore, we cannot reject our null hypothesis. We have to accept the null hypothesis. Or we can say fail to reject the null hypothesis. Fail to reject the null hypothesis, or we accept the null hypothesis. That means our data do not support this statement. And we always interpret this statement. Because of this reason, we say we have no statistical evidence with 95% probability to conclude at least one true mean density is different from the other true mean densities. Why 95%? Because to find this critical value, we used 5% alpha. So the remaining area is 95%. Part E. What's the p-value of the test? Test the hypothesis using the p-value. Do you get the same answer as part D? If your answer is different, interpret again. Well, the p-value is given in the calculator's output. The p-value is equal to 0.0986, which is larger than the alpha value, which is 0.05. Because the p-value is larger than alpha, we once again accept the null hypothesis. Or in other words, we fail to reject the null hypothesis. That means our data do not support this alternative. So we get the same conclusion. All right, that's it about single factor analysis of variance. Thank you.